Hello everyone, welcome to the 8085 practical series. So we are just continuing with practical number 5. In the last session we did two programs, so they were lengthy, so I have extended this in this second video of that is 5b. So in this particular session we will see the first program is multiply two 8-bit numbers stored in memory location 2200h and 2201h by repetitive addition and store the result in memory locations 2300h and 2301h. So we need to multiply two numbers. Those numbers are stored in 2200 and 2201. After multiplication, the data may be of 8-bit or may be of more than 8-bit. So if it is only of 8-bit, it will get stored in 2300 and this will contain 00, and if it is more than 8-bit, the remaining numbers will be stored in 2301. So it is given by repetitive addition. In case of 8085, there is no multiplication instruction. We have addition, subtraction, decrement, increment for the arithmetic operations. We don't have any multiplication instruction. So how do we multiply? So this is the program. You can note down this program. This is the program, the code. Okay, also the hex code is given. Okay, this is the hex code with the program. Okay, now let us understand the working of this. Okay, but before doing this, what is the meaning of repetitive addition? Okay, see, if you want to, for example, if you want to multiply a number like suppose 6 by 4. Okay, so if you want to multiply 6 by 4, it is as good as adding 6 4 times. Okay, so if we add this 6 4 times, it will give the same result what we get by multiplying the numbers. So that is what is called as the repetitive multiplication. So repetitive addition. So we will be doing this multiplication by, like in this case, if you want to multiply 6 by 4, we are adding 6 4 times. That is what we done in our program. Okay, so as we are given, the two numbers are stored in 2200 and 2201. So let me store some number so that we can understand the working. So suppose I store here 6 and here I store 4. Okay, so you have to multiply these two numbers and they are stored in 6 and 4. Okay, then the first instruction, LDA 2200, this instruction LDA, what does it do? It stores the data from the memory location 2200 in register A. So this data 220006 which is there, it gets stored in register A. Okay, now next what we do, move B comma A. Okay, B comma A, so we are transferring the data from A to B. Okay, so this A data will go to register B, so this also becomes 6. Next what we do, next instruction is LDA 2201. Now LDA 2201 will store the data from memory location 2201, that is this data, into register A. So now register A will become 04. Okay, so this becomes 04. Okay. Now next instruction, move C comma A. So C comma A, what it will do, it will store the data from register A to register C. So now we have got two numbers. One number is in register B, other is in register C. So we need to add, of course, 6 4 times. Okay, so we have to do this. So we have taken the first number in B, the other number in C. Then what we do, the next step is XRAA. Of course we know this XRAA, it clears the contents of register A. Whatever is in register A, it gets cleared with this instruction XRAA. Okay, so with this instruction we clear the contents of register A and make it as 00. Okay, and then what we do is we move the same contents A, that is 00, in register D. So I'll just draw this, I'll just make this register D here. I forgot to mention here. So this register D also becomes 00. Okay, now this is the part where we actually do the multiplication, okay, with repetitive addition. Okay, so you can just get the idea. What we do is, first part is add B. What add B will do? Add B means A is equal to A plus B. Okay, add B means A equal to A plus B. So we are adding the contents of A with B. Now A, as we know, is 0 0. You can see A is 0 0. So 0 0 plus this B is 0 6. So 0 0 plus 0 6. So A becomes 0 0 plus 0 6. So A becomes 6. Okay, with this add B. Contents of B are not changed. Only A becomes 6. Then we give the instruction jump if no carry to star. Okay, so this if there is no carry, then this instruction will not be executed. So of course we didn't get any carry, so of course this part will be skipped. There is no increment here in this case. Okay, so then it directly goes to DCRC. What DCRC will do? DCRC will decrement the contents of C by 1. Okay, so as we see, C is 4, it becomes 3. Okay, now it becomes 3. It becomes 3. Then here we see instruction JNZ. JNZ checks whether C is 0 or not. Of course C is not 0, so it jumps to double star. Now where is double star? So double star is actually here. It goes again to add B. It again goes to add B, because C is not 0. So this JNZ will ensure this again goes for addition of B. Now A was add B means A equal to A plus B. Okay, A was 6. Okay, now 6 again, B is 6, so 6 plus 6 becomes 12. Actually this is I am doing in decimal. In 8085 it won't be 12, because it is performing the hexadecimal addition. So the answer will be actually 0C. Okay, but I am just writing in for understanding, I am writing in decimals, so it will become 12. Okay, again the next instruction is JNC. So because carry is not generated, it will jump to DCRC. Okay, again C will be decremented, it will become 2. Okay, and again what we see is it is not 0, again jumps to B. So this add B and DCRC, they perform that repeated addition. So what these two instructions they are doing, add B will add B again and again to with A, and DCRC will decrement C. So after the completion of the entire loop, this 6 will be added 4 times. Okay, so after every loop C is decrementing, so after C will decrement 4 times, it becomes 0 and it will come out of the loop, and by the time it comes out of loop we have added 6 4 times. So this is how we do the multiplication. Now why this instruction, as we are seeing, why this INRD is added here. Okay, why this INR, what this INRD will do? See, if after addition, now this was a very small number 6 and 4, so the answer will be of course of 8 bits. But suppose if the answer, if these numbers are large, then the answer will go beyond 8 bits. So this INRD, whenever a carry is generated, this INRD will increment by 1. Okay, so for every carry it will go on incrementing the answer with 1. Okay, so whatever the answer which is above 8 bit will be stored in register D. Okay, now the final steps. Okay, after after it comes out of the loop, the data which is in A, okay, it will contain the lower 8 bits. So we do STA 2300. Now suppose if we have added 6 into 4, so 6 4s are 24 in decimal. Okay, so if you do in 8085, you will get some different answer, because it will be in hexadecimal. So suppose let us take, like, we are multiplying 10 by 4. Okay, so 10 4s are 40, of course, so we will get this 40 here. Okay, and if there is no carry, so this will become 00. Okay, so if the number is larger than this will be, so STA, what does STA do? It stores the result from register A to 2300. So A contains, after this loop, A will contain the result. So STA, what it will do, it will store the result of A to 2300. So this will get stored here. Okay, and then again move A comma D. Why A comma D? Because the other 8 bits, if the result is above 8 bits, that number is in D, so we store D in A and then do STA. Okay, because we cannot actually apart from A, no other register can directly access the memory location using this instruction. So we only can access the memory location through register A. So this is STA. So that's how this program works. Let us now execute on this on the Jubin simulator. Now before entering the code, we will enter some data in the memory location 2200 and 2201, because we have to add those numbers. So I just reset set. So 2200. I'll just put INR. So I'll just put 10, okay, and INR, and here I'll put 06. Okay, so I'm multiplying 10 by 06. I'm going to multiply these two numbers. Okay, I'll just put one more INR. Now we'll just enter the program now and check the result afterward. Now after entering the code, we will execute the program. So reset go 8000 and then execute. So now we have to check the at 2300. So reset set 2300 INR. So you are getting 60. As we have seen, 10 into 06, so 10 6 are 60. Even in hexadecimal or decimal we get the same answer. We put INR, there is nothing. So because our result was of 8-bit, this is 00 and the previous is 60. So this is how we do this particular multiplication. Now I'll do the next program. Now next is the division program. So we have to divide 16-bit number which is stored in memory locations 2200 and 2201. So because this is a 16-bit number, it has to be stored in two memory location, because one memory location can only store 8-bit of data. So the number which is to be divided is in 2200 2201, and we have to divide this by a 8-bit number which is at location 2202. So the divisor is at 2202, and the number which is to be divided is in these two memory locations combined. Then we have to store, after division we get the quotient. So quotient should be at 2300 and 2301, and remainder should be at memory locations 2302 and 2303. Okay. So this is the program. Okay, first we get the dividend, then get the divisor, then use this DE to store the quotient. Okay, and this is the part which we are doing. You can note down this everything. Okay, and I'll explain the code. This is actually the program. Okay, and this is the code. By before understanding the code, we must understand the idea how we can do division. In 8085 there is no division instruction, but we can perform division by actually subtraction. For example, let us assume we want to divide 16 by 4, and suppose this is a hexadecimal. Let us assume this is a decimal number. Okay, so what we do, we want to divide 16 by 4. So we subtract we do this 16 minus 4 once, so we get 12. Okay, and we have done this subtraction once. Okay, and we check whether this number which we have got the difference. Now this difference 12 is greater than 4, the divisor. So we again go for a subtraction. 12 minus 4, it becomes 8. So we have performed the subtraction the second time. Now this 8 is again greater than 4, so we go for another subtraction. We get 04. This is the third time we are doing this subtraction. Okay, now again this 4. Okay, I should change the equation. Okay, this is greater than equal to and greater than equal to, so this is greater than equal to 4. Okay, so this 4 is equal to 4, so we can go for one more subtraction. So 4 minus 4 is 0. Okay, and this is the fourth time we are doing this. Now this whatever result difference we are getting, it is actually less than 4, so we stop. Okay, after stopping, so this is the stopping condition. We will go on subtracting until whatever the difference is less than the divisor. Okay, now we stop here. Now the thing which we get here, this is the quotient, and whatever we are getting here is the remainder. This is the idea behind the subtraction part. Okay, so how to implement this in 8085? So this is the program, as we can. So here it's the first instruction is LHLD 2200. So before starting with this program, Let us assume we have to do the division, like we have to divide 1060 by 20. Okay, so this is the number which is to be divided, and this is the divisor. So of course this number would reside on this memory location. Okay, so where 60 will be here and 10 will be here, and this 20 we need to store beforehand, before entering the program. Okay, and before executing we need to store this data in the memory location. Okay, so let us assume we have this data and this is the program. We are starting with this, the very first instruction, LHLD 2200H. Now this instruction LHLD 220H, it will store the data from memory location 2200 and 2201, the next one, into LNH respectively. So it means that the data which is at 2200, this data will be stored in register L. Okay, and the next data, this one, will be stored in register H. So this is what we have. 1060 will be stored in this, from this memory location HL, from memory to HL. Next instruction this is LDA 2202. Now this LDA 2202, it actually transfers the contents from memory location 2202 to register A. So this data at 220 to 20 it comes to register A. Then next, this is actually the divisor. Okay, this is the divisor which will divide this 1060. So we are first transferring in A, and then the next instruction with move C comma A, the data from A goes to register C. So this also becomes 20. Next we do some initialization. We do LXI D0000H. Okay, so this becomes, with this instruction LXI D 00 and 00 gets stored in register DE. Okay, this DE register pair. Okay, then actually this DE will actually store the quotient. We'll see that. Then next instruction is what we do. This is the loop where the actual division now starts. Okay, so first of all we transfer the data from register L to A. Okay, now as we know L contains 60. Okay, so move A comma L will transfer the data from L to A. So A also becomes now 60, or 60 becomes 60. Okay, next instruction is sub C. Okay, so to perform division we need to actually subtract. Okay, so what we do is sub C means what? A equal to A minus C. So what we will get? A equal to A is 60 and C is 20, so it becomes 40. So we get 40, which is actually stored in register A. Okay, so this is 40, it becomes 40. Okay. Now next what we do, we transfer the data from A to again to L. Okay, because actually we have to perform subtraction. Okay, but subtraction cannot be done without A, therefore we need to again clear A. Actually this we transfer A to L again. Okay, so what we are actually doing is we are subtracting HL, our dividend, from the divisor C, but we cannot actually subtract HL directly from C, so we need to transfer it to A. So now this, what L will become now? So L will become now 40. Okay, this becomes 40. Okay, now here there is instruction JNC. Okay, jump if no carry. Okay, now because in this particular division there was no borrow, and of course we know that carry flag is also acting as a borrow flag, so there is no borrow, so it will directly jump to next instruction, this one. It will skip this part, and jump to INXD. Now INXD, actually as I told you, DE, it is storing the quotient. How many times we are subtracting will be stored in this DE. Now INX will make this this increment, so with DE is 0000, with INX this will become 0001. So this will actually D and E will have this 0001. Okay. Next instruction, what we do is move A comma H. So we transfer the data from H to A. Okay, so this is what we do, is we transfer the data from H to, so this becomes 10. Okay, and then compare this whatever data is in A. Actually we have to compare H with 00, but because we cannot compare H directly, so we put it in A and compare it with 0 0, compare immediate with 0 0 H. So what this instruction will do, it will compare the data in register A with 0 0 data. Now as we know, A is greater, okay, A is greater than this. So what it will do is jump if no, so 0 will not be generated. When this 0 will be generated when both become equal. So because it is not this A is greater than that, okay, so it will jump if no 0 to star, double star. So double star will again come back to this instruction L comma A. Okay, why are we doing this is actually why this CPI, we are putting H in A and doing this CPI 0 0, because when we are subtracting this HL from C, so a time will come when H will become 0. Okay, when it becomes 0, then we won't we'll just do this L to A and see if it is this L, because when we are decreasing H and L, a time will come when H will become 0 and only L will be left. Okay, so we just need to subtract L, so we put L in A and compare it with the divisor. If it is greater than divisor, then we go for the again subtraction. If it is less than, we stop. Okay, so this will go on until either the contents of HL will become 0 0 0 0, or it will stop if H becomes equal to 0 0 and L is less than C. Okay, the content of L is less than C. Okay, this will continue and it will stop with this either of these two conditions. Now after this condition is satisfied, our division is done. Okay, and next what we do, that SHLD 2302. Now what is this instruction do? It will store the contents of H and L in 2302. Why what we are doing this 2302? Because in the problem it is given that we need to store the remainder at 2302 and 2303. So when we write this instruction SHLD, so whatever is remaining in H and L, it is the remainder part. So we do this SHLD 2302. It will store the data from H and L into 2302 and 2303. Okay, then we perform the exchange. What this exchange instruction does, it exchanges the contents of HL with D. Okay, the content of H will go to D and D to L. H and D are their exchange, and L and E they are exchange. So because D and E, it contains the quotient. Okay, so we need to store the quotient. So DE. Okay, so DE will be transferred to HL. Next instruction is HLD. Actually, this should be, I made a mistake. Sorry, this should be actually 2300. Okay, so because we need to store the quotient at 2300. So this is 2300. So I have to make one more change actually. Okay, so this is HL. This is okay. Okay, this is okay. So here I have to make the change, the mistake. So please take care. This is actually, this should be 2300. Of course, there is change here also. Okay, so after this, what will happen? Whatever the quotient we are getting, it will get stored at 230. Why? Actually, I should have done this before, but because the data was already in HL, so I stored first HL and then I came back for D. So this is how this program runs. Let us now run this program on Jubin simulator. I will start the simulator, and first of all store the data at the memory location. So the memory location is 2200. Okay. Here we have to store the divisor. The lower byte of the divisor is 60 in our case. So we have to divide 1060 by 20. So this is 60, then INR. So this will become 10. Okay, and the next byte will next memory location will contain the divisor, that is 20. Okay, so we want to divide 1060 by 20. Okay. Now we enter the program. Now we execute the program after entering it. So reset, then go 8000 and then execute. Okay, after execution the result would be from starting from 2300, 2301, 2302 and 2303. So first of all we see the quotient. Okay, so reset, examine memory 2300. Okay, INR. So this is 83. So actually the answer is 83, because you can even see, I will show you the result. The result is of course right. We are getting the right result. If you divide 1060 by 20 in hexadecimal, the answer is 83. Okay, and because the quotient is of only 8 bits, the next byte will be 00, and of course there is no remainder because it is a perfect divisor. So this all the next 4 bytes, as you can see, the first byte we are getting at 230083. So 83 is the quotient, because it is of 8 bits, so other 8 bits are 0, and because it is a perfect divisor, so this all the next 4 bits they are 0. Now let us verify the result what we are getting, is it correct or not, by using the calculator. Okay, now we'll verify the result. So this is the, I am using the scientific calculator inbuilt on my PC. So our number is 1060. So this is, you can see the answer here, hexadecimal 1060, and we are dividing this number by 20. Okay, equal to, so this you can see the answer is 83 in hexadecimal. So our answer was of course correct. So you can check the answer here also using this hexadecimal. Okay, because this 8085 works in hexadecimal notation. So that's all for this particular session. Thanks for watching.